Hi everyone. In the previous video, I think we have seen how to do the pre-layout simulation of differential amplifier. So in this video, we will discuss how to do the post-layout simulation for a differential amplifier by creating the layout and performing the post-layout simulation. So what is the first step? Well, this is my schematic diagram for the schematic circuit for differential amplifier. So what we have to do now? First, we have to launch layout Excel, that we already know. So we shall create a new one. So name, let it be the same. Just click OK. Fine. So a layout window will appear. Right. So this is my layout window. Now from here I have to go to connectivity, generate all from source. Here, so usually instance I opens and PR boundary will be auto selected. So this chain and fold, so if you want you can select, or you can need not to select. The only difference between what is this chain and fold is, so the fold will create if there is any common terminal connection between two same components, that is two PMOS or two NMOS, like that, then it will create a overlap on common terminal connection, right? So I'll just show you what is that. It is basically, so in this common circuit, say if you check here, so we have a PMOS1 and PMOS2, right? Here the source connection is common between these two PMOSs, right? So when you create a layout for these two, right, if you don't select the fold option, they'll just create separate layout for this PMOS1 and this PMOS1. If you select fold option, so this source will overlap between these two PMOSs, because there is a common connection, no? So just to not to avoid the extra connection, the source of this PMOS and those of source of this PMOS will overlap. So it assumed to be this looks like to be appears to be a single PMOS circuit. Okay, that is the advantage of selecting the fold option, right? The same way here also, if you observe NMOS and NMOS, so sources are common, right? Here also sources is common. So that's why instead of having 6 layouts for 6 components, we'll get only 3 components or 3 layouts for 6 components by having a common connections. Okay, so let me create a label for 0.05, right? So let me the PR boundary other thing. Okay, now click OK. So when you click OK, so this is the layout that is appearing. So when you click Shift F, now you can see, right? So this is the PMOS circuit, two PMOS layouts, right? And this is a 2 NMOS and this is another 2 NMOS. Because see, if you observe here, I'll just zoom it out. See, this is one PMOS, right? And this is another PMOS. Because between these two PMOSs, so source is common, that's why the source is here, this source is overlapping, so having a single connection from here. Okay, that's why the fold option will be useful. Otherwise usually you will have a separate connection for this as well as this. Okay, this can also be done fine. So I'll just separate this. Now shift, so I'll take this PMOS on the both side. Okay, so and let me take V2 and V out on this side. I'll just separate this. Okay, just to have a separate layers for all the connections. Okay, now we have to give the connection for all the connection, we shall come from the beginning. Okay, so what we do first, if you observe here, the source of the PMOS, both the PMOS are interconnected, that is given to VDD, right? So if you observe here, see the source and source are overlapped, so this is the connection, right? This has to be connected to VDD, right? So just to observe here, see, so if you move this pen, it will show you where you have to connect this. See, it is showing to VDD connection. So okay, so I'll just take this on this side, so just to place the via contact. Why? Because this is the PMOS circuit, so PMOS layout, so all the PMOSes has to be connected, sorry, created inside the envel. So for that, so first I have to go to create, select via, select envel. Okay, because I have to create this inside the envel. Get height, so exactly above this we have to create the layout, so I place it here, right? So let me flatten this. So I'm going to flatten this first. Now what we have to do, I have to stretch this because the NMOS should be inside the envel. So this is the envel, so this PMOS should be inside the envel, so I have to stretch this up to here. So I'll select stretch on both the side, right? I've successfully created this PMOS circuits inside the envel, right? So and again we have to extend this because it was showing the oxide, minimum oxide layer, right? Yeah, now we have to give the connection to this pin, right? So this is the VDD connection, so I'll select path, so I'll give a connection again. So to this I have to connect the VDD pin. Okay, so that is what I am doing now. Now the VDD connection is done. So if you observe here, see this connection I have given. Now what we have to do, we shall take the output connection, right? The drain of one PMOS is connected to the drain of another NMOS, right? So both are interconnected and that has to be given to output, right? So how to check that which is the source and which is the drain, whether this PMOS drain or this PMOS drain? So usually we'll get confuses. Because of that, what we do is we shall take Vout pin, so it will only show where you have to connect this pin. See, it is showing it, so we have to connect here. This is the one end, so another end is, see, it is showing here, so we have to connect these two ends. To that we have to give the Vout connection, right? That means this is the NMOS drain, one drain, and this is the PMOS drain, so this has to be connected, and for that we have to give the Vout connection, right? So we will do that now. So how to do that, take path, shortcut is P, right? So take path, just extend here, so just give a connection here, right? So now, so Vout has to be connected to on this line, right? So this is for your understanding, I'm just putting on the metal, or you can extend this metal and you can connect it, just for your understanding. Okay, fine. So what we did, this VDD connection has been given, fine. Okay, now, okay, so this connection has been given, so this has to be given to Vout, so that connection I have given, right? If you observe here, says this. Now we shall take the this connection, right? So before that, if you observe here, see the gate of PMOS and gate of PMOS are interconnected, right? See, gate of PMOS is connected, so we shall give that connection first. So in this PMOS, this gate means polysilicon and polysilicon are interconnected, right? So what shall we do now, we shall interconnect this first, right? So we shall take the path, extend, see it will only showing the connection. See, this is supposed to be connected to this and this pin and this pin as well as this, right? So what we do now, so we'll take this connection, we'll give the connection, see it will only automatically gives. So you have connected gate to gate. Now the drain of PMOS and drain of another NMOS should be interconnected, right? So if you observe here, see, so one drain is already connected. We left with only one drain. So this drain has to be connected to this drain, right? So because if you just check here, see, the path is developed, right? So it has to be on this, and it has to be connected to this pin, right? Now we have connected drain and drain. So this is the drain and drain connection is given, but we have left with this connection, right? So this gate and drain should be short circuited. So that we have not done yet, right? If you observe here, see, metal can pass on the polysilicon, but there is no contact between these two. If you connect these two, then it will give the connection, right? How to give the connection? Just take a simple via contact P1 poly, sorry, M1 poly, just place it here. Okay, so how to do that? Select via M1 poly, take it and place it on the via contact, right? It is showing a minimum spacing, so you can place it anywhere here. It's not showing any contacts, so any spacing errors are just placed here, or you can place anywhere on this without showing any placing errors. Okay, now this connection has been done. That means this connection has been done, right? Now we have left with V1 connection and V2 connection, right? If you observe here, NMOS gate 1 is connected to V1 and NMOS gate 2 is connected to V2, right? So we shall check now. So how to get that connections? Just move this V1, so it will only show you, right? V1 connection should be given here, and V2 connection and V2 connection should be given here, right? So if you observe here, see, it is showing at this point, right? So if you observe here, so this is the connection we have to give, right? So that means V2 is connected to this pin and V1 is connected to this gate, right? So we'll do that now. So how to do that? Select path, take V1 and extend towards this place, and again same thing, take gate V1 and extend it here, right? So now you need to connect to metal and poly, you need a contact, right? So I'll take via contact. M1 poly is already selected, so just place it here. It is showing minimum area error, we will extend that later. So here also minimum spacing here. Now so we have to flatten this, so I'll flatten it again here. This one also I'll edit and flatten it. Okay, now both are flattened. So but in order to connect this, I need to extend this pin. So how do I do that? Select stretch, extend this, okay, like this. Now I have extended this. Again in the same way I have to extend this also. See, so I've extended both. Now I'll place V2 here, right, because the connection to this here. So I'll give connection V1 and V1 here, right? This connection is for this pin, right? I have given here, right? So I've given both the connections, V1 and V2, right? So now if you observe, so this connection has been given and this connection also has been given. Now what we left with? These two connections, right? See, this is the common connection between NMOSes, right? Common source connection. So that connection is given to the drain of another NMOS, right? So we will see that. So this is this connection, right? So this connection has to be given to what, right? So we shall check that. So select path. If you check here, see, it has to be connected to this point. It is only showing. We'll take that. See, it will only take the automatic connection. Now we have done with this connection, right? So that is, we have done with this connection. Now in the last module, in the last layout module, so first we'll take this connection, right? So gate and gate of both the NMOS are interconnected, right? If I take here, see, so we are left with all the connections of these two modules. Now we left with this. So here the gate and gate are short circuited, right? So that means these two polysilicons are short circuited, right? So what shall we do? We will connect this by taking the path. See, it is taking the automatic connection, so I'll just give that, right? Now this gate and gate connection is done, right? Now we left with this IDC connection, right? So we have one more pin, that is IDC. IDC has to be connected to one of the NMOS drain, right? So we will check that where we have to connect that. Here my IDC pin is there. See, if you check here, see, it has to be connected on this point, right? I'll take this. See, it has to be connected here. So I'll take the pin here. See, so you don't have to get confused if you know the connections properly. So it will only automatically connects. Fine. So if you check here now, so these two pins should be connected, right? So what we do, we'll take path, give the connection. It will only take automatically, right? Now successfully given the IDC connection. Now we have left with only one connection, that is this, right? There is a common terminal connection between these two NMOSes, and that connection should be given to VSS, right? So how do we do that? From here, see, there is a common connection between these two NMOSes, right? That is, this should be given to VSS, right? So how do we give the VSS connection? This should be given via P substrate, right? So how do we do that? Go to create, and via our shortcut is O, select M1 P substrate, right? Select and hide. Here we have to give the connection, right? So I'll just place it here, right? Then we have to extend this oxide layer. For that I have to go to hierarchy and flatten it. Now we have to extend this. Stretch, extend all the layers, right? Now I have extended successfully. Now I need to interconnect these two, right? So how do I connect? Using path, right? See, I have connected. Now this has to be connected to this pin. Okay, so that is how I have to place properly. Just place it here. Now I have successfully given all the connections. Now we will check for the DRC. First I'll save this. I have given all the connections. If you observe here, see, I have given all the connections: IDC, V in, V out, this connection, this, as well as last. Now we shall check for DRC. Go to Asura, run DRC. Click OK. Now click OK. Yes. So there is a one problem. So we shall check that. Metal 1. So here, okay. This there's a slight change in the width. So what we do now, we'll select this, we'll place it properly, right? And also here we have to check. So we'll just delete this, then we'll give a connection. Okay, select path, then I'll take path here, yes. Now I have given the proper connection, so I'll just save this. Again I'll go to run, DRC, click OK, run. Yes, no DRC error found. Now I have given the proper connection, I have used all the uses properly. Now what is the next step? I have to check for LVS. Run LVS, select OK. Now we'll wait for LVS. If any mismatches are there in that. Yes, so no mismatches are found. Right click as. So schematic and layout are matched. Now once we have done this, the next step is we have to extract the parasitic components, right? So for that run QRC. So check for all the settings. So I think I have done all this already. So filtering, yes, netlist, okay. I think I've done all the settings properly. I'll just go to OK, click OK. Now yes, so QRC completed successfully. So let's click OK. Just to view that extracted file, I'll go here in the schematic, I'll select AV extracted. So just click OK. You can see the AV extracted file here by Shift F. See all the tiny particles, you can see, right? Yes. Now just close this. The next step is we have to perform the back annotate process, right? How do we do that? So go to file, create new, a cell view. Here the name you have to select is test schematic file, right? This is a test file that you have created for preload simulation. So instead of layout, I'll select config, right? Click OK. Yes. So here use template. Here select spectre. Click OK. Now instead of my view, I'll select schematic. Okay. Now click OK. Now under we found schematic, I want to use what? I want to use the AV extracted file, right? I've just typed it, click OK. Now it is asking for the update, right? So just click update. It's asking for the save and the synchronization, so click OK. Now save this and close. Now we have done the back annotate successfully. Now we have to open the test circuit and we have to perform the post layout simulation. So then go to file, open, select amplifier test, configure file is already there, click OK. Configuration I don't want to view, top cell view I want to view, yes, click OK. Now the test circuit will appear, right? This is the test circuit. Just to verify whether this symbol has the AV extracted file, just right click and descend read, select descend read. See, you have a AV extracted file here. So don't click OK, just cancel it just to verify, confirm that, so whether we have a AV extracted file or not. So now we have successfully back annotated. We'll verify for the post layout simulation. So how do we do that? Launch layout Excel, launch ADL design environment, Now here you can choose the analysis one by one as we did in preload simulation. Otherwise you can directly load the states if you would have saved those states or those analysis in the preload simulation. So while you're doing the preload simulation, you can save those states. Usually that will ask for saving. Right? If you save those states here, you can directly load those analysis, and you can directly perform the simulation. Right? So here I have saved already, so I'll just load those states. Right? Click OK. Now see, all the settings are loaded. Now I'll just perform the simulation. See, now I have got the result for transient analysis, AC response, AC analysis, as well as DC analysis. Right? So here you can check with, so how much gain I am getting, right? How much it has been reduced or how much it has been lost. So what is the difference between preload and postload simulations? You can note down all the values, right? And you can verify the results. Okay, so how do we do that? Just print this file. Right, so I'll go to test1. Inside test1 I'll save this. So common differential amplifier, instead of pre-layout I'll give it as post layout. Okay, yes, save this and print. Right, so this is the post layout simulation of differential amplifier. Okay, just practice this. If you get any doubts, you can ask me. Okay, at the end. Okay, thank you.